So there are two important properties and important theorems in Laplace transformation using which we can find out the value of the signal initially and in the steady state. Alright, so the first theorem says that your function's value in the time domain initially is equals to your Laplace transformation times s, which is valued at s equals to infinity, which is evaluated as s equals to infinity. And another theorem says that your function's value at infinity is equals to s times your Laplace transformation, which is evaluated as s equals to 0, s tends to 0. Now we're going to prove that theorem. First of all, very easy proof it shares, and we know from bilateral, we know from Maclaurin series that x of t is equals to x of 0 plus x dash of 0 t plus x double derivative of 0 t square over 2 factorial plus dot 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 plus x n of 0 tn over n factorial plus dot 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 and ultimately u of t to make it 1. Alright, this is simply Maclaurin series or Taylor series continuation. Alright, so what is going to be x of s? Simply taking this equation in the Laplace domain. So it's going to be x of 0 times ut, which means 1 over s, then x dash of 0 times tut, which is going to be 1 over s square, plus x double derivative of 0 t square by 2 factorial times ut, which is going to be 1 over s of cube plus dot 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 going on x n of 0 times t to the power n over n factorial and ut, which is big, which will become 1 by s over n, and plus going on. All right, now we are going to multiply the both side by s. All right, if we multiply both side by s, we get x of 0 plus x derivative of 0 1 by s plus x double derivative of 0 1 by s square plus higher terms of 1 by s, higher terms and power of 1 by s, right? Now if we limit it as limit s tends to 0, s, now if we limit it as s tends to infinity, then limit s tends to infinity s of xs. Now on the right hand side, all the terms that have 1 by s or 1 by s square and the higher powers of 1 by s are going to become 0, because 1 by infinity is 0, so what's going to exist is only x of 0. So our first theorem is proved that if we want to evaluate our signal at x of 0, we simply multiply our Laplace transformation by s and limit it by s equals s tends to infinity. Alright, now we're going to prove our next theorem. Alright, next theorem is about finding the function's value at infinity. So we know that Laplace transformation of x derivative of t is equals to 0 to infinity x derivative of t e to the power minus st and dt. This is our Laplace transformation of x derivative of t, and it is equals to s x of s minus x of 0. We have derived this in the last video. Alright, so now if we take a limit, that limit s tends to infinity 0 to infinity x double x dash x prime t e to the power minus st dt, and taking limit on this side also, s x of s minus x of 0, then what do we get? If we evaluate the limit, then if we evaluate the limit, then we see that e to the power minus st, which will become simply 1, right? So there is no need to write this, and x derivative of t dt is integral is going to be x of t simply, and evaluated at 0 to infinity. There is no s here, so it's going to survive without the limit minus x of 0. And if we put on the values evaluation, then x of infinity minus x of 0 is equals to limit s tends to 0 s x of s minus x of 0. If we cancel out x of 0, then we get x at the rate of infinity is equals to limit s tends to 0 s x of s. So our second theorem is also proved. So if you want to evaluate a function at infinity, you multiply your Laplace transformation by s and evaluate it for s becoming 0. Alright, now we're going to use that theorem. Alright, so it has been asked that this is our Laplace transformation of some unknown signals, and we want to find out the signal's value in time domain value at t equals to 0 and infinity. So what is y equals y of 0? Y of 0 is going to be limit s tends to 0, s tends to infinity, s of ys. Remember, there is a transparency between 0 to infinity. When we want to know value at 0, the limit should have been infinity. So limit s tends to infinity, s 10 twice s plus 3 divided by s square plus twice s plus 5. And then we know our old formula that if we want to evaluate at s equals to infinity, then you should take the highest power in common. So the highest power here should be 10 times 2s square plus 3s and s cube plus 2s square plus 5s. If you use the shortcut, you can easily do it. Just take s cube common here and s square common here. 2 plus 3 by s and s cube, 1 plus 2 by s cube, 2 by s plus 5 by s square. As s tends to infinity, these two terms will cancel out very easily. This will become simply 2 and this will become simply 1 because other term will become 0, right? And what do we get ultimately? Limit s tends to infinity, 10 into 2, 20 into 1 by s. Ultimately 1 by s, so that means 1 by infinity will be 0. So our initial value of our function is 0. Now if we try to evaluate it at y tends to infinity, then it's simply going to be limit s tends to 0, s 10 twice s plus 3, s times the Laplace transformation, s square plus twice s plus 5. Alright, so it's going to be if we put all the values of s right now, s gets cancelled out. Then if we put on our values of s, it's going to be 0 0 0, so 30 over 5, 10 times 3 over 5, so it's going to be simply 6. Our value is evaluated. Now this is a very simple Laplace transformation of simple polynomials and functions in the upper portions. Now there is a thing you should know. Suppose I give you the function s plus s square plus omega naught s square. Now what is it? It's the it's the Laplace transformation of cosine of omega t with ROC as real part of s is greater than 0. Alright, that's the ROC of this Laplace transformation. So if we try to evaluate it as consider it as ys, and if we try to evaluate the time domain function at infinity, then we need to put the limit s tends to 0, s of ys, limit s tends to 0, s square over s square plus omega naught square. Now you might think that this s square, if we put 0 in the numerator, 0 omega square in the denominator, it should be 0, but this is wrong. As limit s tends to 0 is not in the ROC, we cannot use that limit. We cannot evaluate the function in that limit. If we evaluate it, you can find out something, but that's garbage answer. Alright, so that's unnecessary and that's irrelevant. So you can see from time domain also, its time domain function would be cosine of omega naught t, which is undefined at infinity. So the lesson I want you to know is that if some value of either 0 or infinity is not in the ROC, you cannot find out the corresponding value in the time domain. If 0 is not in ROC, then you cannot find out y of infinity. If infinity is not in ROC, then you cannot find out y of 0. That's something you should know. Alright, now I want to know about periodic signals. Alright, this is some random periodic signals, not sine, not cosine, whose integration is very difficult. Now how can I find out the Laplace transformation of this periodic signal easily? Alright, so that's our target. It can be thought that the first period as a signal, second period as a signal, third period as a signal. Alright, first period being called x1 of t, then this total signal is going to be first period plus second period plus third period. All right, what is the second period? Second period is a shifted version of our first period signal, right? Second period signal is going to be our first period signal shifted by t. Third period signal is going to be our first period signal shifted by 2t. All right, and it's going to go on like this. So what's the ultimate Laplace transform of this signal? It's going to be x1 of s plus x1 of s, as it is shifted by minus t, is going to be to the power minus ts, plus x1 of s e to the power minus 2ts, plus going on. So if we take x1 of s in common, 1 plus e to the power minus ts plus e to the power minus 2ts, plus going on. Now you are born to know what the series converges. All right, and when converges, this is the series of 1 minus e to the power minus ts, provided that if absolute value of e to the power ts minus ts is less than 1. So that's the hierarchy. That's what we want to do if we have any random signals except sines and cosines, pure sines or pure cosines. We want to take the first period, we want to find out its Laplace transformation, and then simply multiply by 1 over 1 minus e to the power minus s times the time period. All right, this is the time period of our signal, and then we'll find out the whole Laplace transformation of our periodic signal. Now we will do some example. We will do an example from which is given in the section 3 section C CT. All right, it has been given that there is a half wave rectified signal. It's also periodic, right? There is a half wave rectified signal, and it has been asked to find out what's this Laplace transformation. All right, so how can we find out its Laplace transformation? Our first goal should be to find out the Laplace transformation of the first period signal, and it has been given that the full wave rectified signal shares a time period of t and an angular frequency of omega. All right, and an amplitude of a. Good, so far so good. So our first target is immediately to find out the Laplace transformation of just our first period signal. So what's our first period signal? Our first period signal can be thought of as the positive portion of a pure sinusoid. All right, so it can be thought of uh, of a sinusoid a sine, but remember that the sinusoid will have double the frequency, double the time period than our first period, but than our given periodic signal. So it's going to have half the angular frequency. So it's going to be omega by 2t, and which is valid till 0 to t to t, 0 to small t to our capital T. So right till then, so till now it's all okay, fantastic. So this is our form which we want, because we want to do the integration in sines. You know, if we convert it to sines, we can take it to Euler and so on. So what's this Laplace transformation? Laplace transformation is going to be 0 to infinity a sine of omega by 2t e to the power minus st dt. Now 0 to infinity, the limit is 0 to infinity, but after the value t, it's all 0, our first period signal. So it's going to be only t, right? And as it is sine, it begs to take it into Euler. So it's going to be 0 to t imaginary part of e to the power j omega by 2t e to the power minus st dt. All right, a imaginary portion of 0 to t e to the power minus s minus j omega by 2t dt. All right, so far so good. Then we see, if we try to validate the integral, a imaginary part of the minus is taken on here, s minus j omega by 2. All right, and then we get e to the power minus s minus j omega by 2 evaluation from 0 to t. Good, so far so good. We want to continue on this way. It's minus a imaginary part of 1 by s minus j omega by 2, and then we get e to the power minus s minus j omega by 2 capital T minus when you j omega by 2 capital T, and when you put 0 is going to be 1 simply. Alright, imaginary part of 1 by s minus j omega by 2, and if we take them parts by parts, is going to be e to the power minus st e to the power j omega by 2t minus 1 e to the power j omega t is simply 2 pi, so 2 gets cancelled out, is going to be e to the power j pi, and the famous theorem says e to the power j pi equals to minus 1 from all our stick forward. So I'm going to remove it and give a minus sign here. If I take the minus sign in common, then this minus and this minus will get cancelled out, so overall I get a plus sign. Now I need to take the imaginary portion of it, right? A imaginary portion. To take imaginary portion, I need to multiply by the complex conjugate. Then it's going to become s square plus divided by omega square plus 4 s plus j omega by 2 1 plus e to the power minus st. Alright, then imaginary portion is simply going to be omega by 2 s square plus omega square by 4 1 plus e to the power minus st. This is the Laplace transformation of our first period signal, right? Then what is going to be the Laplace transformation of our whole signal? Is going to be x1 of s 1 by 1 minus e to the power minus ts. So it's going to be a omega by 2 1 by s square divided by omega square plus 4, then 1 plus e to the power minus ts divided by 1 minus e to the power minus ts, and this is the Laplace transformation of our full signal. So you see, the working rule is that whenever it's given that some unknown periodic signal, you need to first find out the first period's Laplace transformation, and then you multiply it by this factor, this factor, and you find out the whole periodic signals Laplace transformation. This is very useful and very handy. Thank you.